Hello everyone and welcome to our video today where we're talking about Gen Chem Chapter 8, Gases. I think you can see the whole board, yes. Okay, so let's get started. So first, I thought it would just be important to go over the different phases. Now let me move this so you can, actually I'll say it first and then I'll move the camera. Okay, so we have our different phases here, right? So solid, liquid, gas. So if we're going from a solid to a gas, that is sublimation. You can't see. That is sublimation, okay? Pause that, take a picture so I can put the camera down and we can talk about it. Okay. Let's keep going. Okay, so from solid to a gas is sublimation. From gas to a solid is deposition. From solid to liquid is fusion, and from liquid to solid is freezing. So those are just some important things to recognize in this chapter and as we carry on with this content. So we also have something called a phase diagram, which kind of shows us solid, liquid, and gas and where those things exist. You can see that there's two kind of points here. I will just ignore the dotted line for now. But you can see this is temperature down here as well on this axis. So this point right here is called the triplet point, and that is a point where all three phases coexist. So at that point you have solids intersecting with gases intersecting with liquids, right? So at that point all three phases coexist. It's kind of cool. Oh yeah, we also have supercritical fluid, which we don't cover on the MCAT, but it's part of the phase diagram anyways. And then we also have this point up here that I labeled B, and B is the critical point, and that is where there's no longer a difference between gas and liquid. Okay, so we can see that this solid boundary line is kind of going in this regular direction, right? However, when we're looking at the phase diagram for water, that changes because water, we're looking at H2O. Water is, the liquid type. So if we're looking at H2O, that changes because the density of water, so the density as a liquid, is greater than the density of H2O as ice in its solid form. So that's why when we're looking at phase diagram for H2O, we would see the line kind of go back that way. So otherwise it follows the same trends except for this solid boundary line there. And yes, so all the other, I'm going to erase it now once we made that distinction, but other phase diagrams look like this. Oh, and that's also why, ice floats and why ice expands as well when you freeze it, right? Okay, so we're going to come back to Graham's law in a moment, so let's go to this side over here. So here we have a heating curve. So I wish the pink was a little easier to see, so I might, let me actually bring you closer once again so that you can see it. Pause it, take a photo so I can put the camera back. Okay, so let's talk about it. Make sure it doesn't fall here. Give me one moment. Okay, so this heat curve. Sorry, it looked like it was gonna fall. Okay, so this heating curve, right? So we have temperature increasing here. Here we're showing the melting point and the boiling point. Here, and we also have heat added. This axis, I don't know why I forgot to label the two axes, I'm sorry. So heat added is actually gonna be on this x-axis here. So what we're looking at is a substance through these some phase changes. So we have this heat of fusion here in this box, and then we have this heat of vaporization. And what this is really showing us is that the temperature does not change during a phase change. So it could be, this says it's going to be solid, so it's going to be a solid until it gets to the melting point. When it gets to the melting point, right, fusion, solid to liquid, when it gets to this melting point, the temperature is not going to change just for a brief moment until that phase change occurs and now you have a liquid. And then that liquid is going to continue being liquid until it gets to the boiling point. At the boiling point, again, the temperature is not going to change at that exact moment where there is a phase change, and then your substance will continue to be a gas. So that is definitely important to know, because if you're using the Q equals mc delta T equation, so if you haven't seen the thermodynamics video in physics chapter, I want to say 3, go back to that. Thermodynamics in physics, we talk about how to use the equation Q equals mc delta T. But for now, just make reference to it. When you're using that equation, if you have phase changes in there, you actually need to add the energy of the phase change to that Q value, because you're not just, because the temperature is not changing, you still need to account for the energy it takes, or the heat added that it requires to actually change the phase. Okay, so let's just go back here. So if you require heat or energy to change the phase, but the temperature does not change. That equation is Q equals N delta H, where N is the moles, right? And then delta H could be delta H of fusion, or the delta H of vaporization, whatever it is, depending on the phase, you would write that. And then you still have the Q values, Q equals mc delta T, during when it is a solid, when it is a liquid, when it is a gas. So when those things happen, you're going to use Q equals mc delta T to represent the Q of those moments. But you, like I said, you're also going to need to include the Q values of, the phase changes. So I was going to include this whole thing to figure out the amount of energy, if I was going to do this whole thing and figure out the amount of heat, Q, right? If I was going to find Q for this whole thing, I would need to do Q as a solid plus Q using this equation, the N delta H of fission, plus the Q value as liquid, plus the Q value for vaporization, so N delta H vaporization, plus the Q as gas. So you need to add all those things to determine the total from the phase change of the solid to gas of a substance. So just be careful of that. If it says that there's a phase change, or the heat of vaporization, heat of fission, make sure you're paying attention to that, and that you can add that to whatever your Q value is in just a regular state. Hopefully that makes sense, but just something an important point. Okay, so now we're just going to talk about some vocabulary. So we have volume, which equals the space gaseous substances occupies. And let me see here if I can move this. Okay, so I used kind of some abbreviations at the ends here because I didn't really have space, but I'm going to explain them. So the volume, IMF, is intermolecular forces. Okay, so the volume is the space that gaseous substances occupies. Is sorry, I just want to gather my thoughts for a second. So the volume is going to be indirectly proportional to MIF. And what that means in layman's terms is that if you're increasing the space, right, you're increasing the volume, that means you're going to decrease the interactions of the molecular forces, right? Which is why they have an inverse relationship. So that's why this symbol here I was just using as indirectly proportional, okay? So I'm going to explain a couple of them. Then the other ones, if you use what I did explain, you can kind of put those pieces together. So pressure is a force exerted by gas particles on a surface. That is going to be proportional to the intermolecular forces, because if you increase the pressure, right, you are increasing the interactions. That makes sense. So that means that the intermolecular forces will be proportional to pressure. If you increase pressure, you increase interactions. Okay, now density. Density is rho over mass times volume. I think I wrote this the wrong way. That is not the case. Let me write that out. It's density, the rho equals mass over volume. I always remember it's because it's like a heart. It's like, I love density. So density equals M over V. So it kind of looks like a heart, right? Okay. Sorry about that. So let's continue. So density, mass over volume, is the measure of how condensed a substance is. So that means that the external pressure will be indirectly proportional to density. The external temperature will be directly proportional to density, which means also that the intermolecular forces are going to be proportional to density. Okay, now we're at vapor pressure. So vapor pressure equals the force exerted by a gas particle that is vaporized. So we have external pressure is proportional to the vapor pressure, and we have intermolecular forces is indirectly proportional to vapor pressure. So that means if the vapor pressure goes up, the intermolecular forces will go down. And now we're on to boiling point. So boiling point is the temperature at which condensation / vaporization occur. And this is an interesting one. And so is melting point or freezing point. So let's do boiling point first. So boiling point is the temperature at which condensation / vaporization occurs. So in this case, when something's boiling, right, if you think you're boiling a pot of water, you would have the external pressure is directly proportional to the boiling point. And so is the intermolecular forces. So that means as boiling point increases, the intermolecular forces is proportional to that and also increases. So something has a higher boiling point, that means it's harder to break the bonds to bring that substance to a boil because there are higher intermolecular forces. Or it's more so the other way around. Because there are higher intermolecular forces in a specific substance, it requires a much higher temperature to be able to break those bonds. That's a really important concept. Okay, so now we're on melting point and freezing point. So that's the point at which fusion or / crystallization occurs. And the external pressure is directly proportional to melting point / freezing point, and the intermolecular forces are also directly proportional to that. So I know there's a lot of proportionalities and a lot of like really comprehension that has to come with this part of the video, because it really will take you a minute to like sit there and really understand why these things happen. Like I said with the volume, okay, if you're increasing the space, that means you have less interactions, which means it makes sense that that relationship between volume and intermolecular forces is inversely proportional, right? So if you go through that with everyone and really sit there and say, okay, if I'm increasing the pressure, that means I'm decreasing the volume, right? What happens when you decrease the volume? The temperature will increase. And you really have to sit there and go through these scenarios to really understand those proportionalities. But once you do it, you will understand and you'll be able to really comprehend things better. That's what I had to do, especially with like the boiling point and the melting point. I was like, what does that really mean? Like when you give it a meaning and some context and you understand why those relationships are like that, it makes it way easier. Okay, so now we're on to kinetic molecular theory. And the kinetic molecular theory states that ideal gases have no intermolecular forces. So we make that assumption. Oh, the orange is a little hard to read too. Okay. Also makes the part of this theory says that the ideal gas particles are negligible in size. It also says ideal gases average kinetic energy is proportional to temperature. So, if again, proportionality, right? If you increase the temperature, that means you have more kinetic energy. That makes sense. Particles have more energy themselves because the temperature is higher, they're moving around more, they're more excited. So, that is that. And then finally, the ideal gases situation is favored in higher temperatures and decreased pressure. So whenever you have that situation, you're closer to an ideal gas at a higher temperature and decreased pressure. Okay, so now let's look at the units. So for pressure, 1 atm equals 101,000 pascals. Okay, 101,000 pascals equals 760 mmHg, right? Millimeters of mercury equals 760 torr. Those are definitely conversions that you need to know. Then we have volume, okay, can be measured in 1 liter, equals 0.001 meters cubed. 1 liter also equals 1,000 milliliters, and that also equals 1,000 centimeters cubed. And now for temperature, you have temperature in Kelvin. The temperature in Celsius is the, let me say that again. The temperature in Celsius would be, if it's given, you need to add 273 to that to get your temperature in Kelvin. Okay, so you have your temperature in Kelvin or your temperature in Celsius. If you're given the temperature in Celsius, just add 273 to that number, and then you will have your temperature in Kelvin. Okay, another really important point, you have STP, okay? That is at 0 degrees Celsius and 1 atm. But that's different than standard state. Standard state is at 25 degrees Celsius and 1 atm. So please make that distinction, because they might say, different things like that in your question time, so just really pay attention to that. STP is at 0 degrees Celsius and 1 atm, and standard state is at 25 degrees Celsius and 1 atm. Okay, so now we're at the last part of this video. We're talking about the gas laws. So we have Boyle's law, which says that volume, again, more proportionalities. It's basically using a lot of the concepts that we talked about up here, but just putting them into equations that we can use. This was more so for understanding, because you know what volume is, you know what pressure is, you know what density is at this point, right? You're studying for the MCAT. But so the important part is knowing like how these things affect one another, and what more information you can gather from one of these things. So let's go back to these gas laws. We have Boyle's law. Boyle's law. It says that volume is directly proportional to 1 over P. So another way of saying that is indirectly proportional, right? So that equation for that is P1V1, so first pressure times first volume, equals P2V2. So if you're given P1, V1, and P2, you can solve for V2, right? Or things like that. Okay, and manipulate that equation. Charles's law says that temperature is proportional to volume. So that means you're going to have V1 over T1 equals V2 over T1. Then we have Monton's gas law, which says that temperature is proportional to pressure. Okay. If you have increased pressure, you have increased temperature. That makes sense. But that also means in terms of an equation, you have P1 over T1 equals P2 over T2. Okay? Okay. Then all these laws together, we can use the combined gas law. So these are just individual kind of situations, right? But if we use the combined gas law, we can do much more. So the combined gas law is P1V1 over T1 equals P2V2 over T2. Okay, in the combined gas law, make sure pressure is in atm. Well, all these things really, but pressure is in atm, volume is in liters, temperature is in Kelvin. So you got to use these units in conversions to make sure that you have the correct units in these equations. Okay, so we also have Avogadro's law, which says that the volume is proportional to the moles of gas that you have in that container. Just like think about that for a second. The volume is proportional to the number of moles of the gas that you have in the container. Okay. Then you have the ideal gas law, which is PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is this gas constant here, which is 0.08 liters times ATM over moles times Kelvin. Oh. And then the temperature. So PV equals nRT, ideal gas law equation, super important. But with that, we know that in reality, not all of our gases are going to be an ideal situation, right? So the real world gases, you just need to remember that the ideal world is greater than, right, the real world, which means the pressure of the ideal gas is going to be greater than the pressure in reality. And the volume of the ideal gas is going to be greater than than the volume in reality. So just know that when we're talking about real world gases, that those relative to the ideal gas law or relative to the real world gases, how those pressure and volume, how you should kind of look at that in context. And then we have Dalton's law. Okay, Dalton's law talks about partial pressures. So we have partial pressure of A, let's just say A is the molecule or a specific compound, right? So we have a partial pressure of A equals XA, which is the mole fraction, times the total pressure. So how do you find this XA? How do you find this mole fraction? So the mole fraction is the moles of that specific substance that you're looking for divided by the total number of moles in the the gas mixture or things like that. This usually comes up in problems. You say you have a container with these different gases in it. What's the partial pressure of this one specific gas in this mixture? So that's when you use these equations. And then finally, over here, let's move it back. Okay, down here, let me move it. Down here, we have Graham's law, which is related to the rate of diffusion. And the rate of diffusion is basically saying that heavier molecules will diffuse slower, right, than lighter molecules, because lighter molecules will be able to move faster. So what this means is that they're saying that the rate of diffusion is, like I said, related to the molecular weight. So you have V2 over V1 equals molecular weight 2 over molecular weight 1 all square rooted. So that again is just talking about the diffusion of gas molecules. So if a gas is lighter, it will diffuse quicker, right? Because lighter things can move quicker. So that is the last part of this chapter. Hopefully a lot of this made sense. If you have any questions, as always, put them below. Hopefully this helped you go through some of the concepts and you understand all the proportions behind me. If you do, you're in good shape. But if you don't, that's okay. Just sit down and really think through the context of when those proportions might be true or what happens. And honestly, what I do a lot of the times, what I have to do is like put in numbers in the equation. Like I usually use like 10, 5, and 2 in an equation, and I say, okay, if 2 equals 10 over 5, and it says it doubles the denominator. Okay, so I double the denominator. What does that do to my number on the left? Like, just kind of play around with it to really understand and see how those numbers change, because I know the proportions can be confusing. But I will see you in the next video. Keep going. You've got this. You're doing great, and I will see you soon.